Hello and welcome to the Introduction to the UVM. This is a Verification Academy course that will teach you the basics of the Universal Verification Methodology, and I am Ray Salemi, a Senior Verification Consultant with Mentor Graphics. I've been with Mentor Graphics for over 10 years, and I'm the author of two books on verification, one called FPGA Simulation, that's an introduction to the topics of advanced verification, and the other is the UVM Primer, which, like this course, is an introduction to the UVM. Both of them take you step by step through the process of learning more either about verification in terms of FPGA simulation or the UVM, as in the UVM Primer. This course will do the same thing. So why are we here? We're here because our job as verification consultants, or as engineers in general, is to affect the roadmap for our companies. If we think about what our company does, we create products, and our advantage in the market is our ability to create better products more quickly. So whenever we go and visit with our customers, we say, well, here is our product roadmap, here's the amount of time it's going to take for us to come out with all of these new and better products, and that naturally is going to go up and to the right. We're going to have more better products as we go through time. Our job as engineers is to take this arrow and turn it into this arrow. We want to have even better products in an even shorter amount of time. So we want the slope of that arrow to go up higher. And in order to do that, especially when we're doing work with ASICs or FPGAs, is we want to be able to deliver these products faster and with more functionality. Our job as verification engineers is to reduce the risk of delivering products to market. We want to reduce the risk of several things that could go wrong. One is that we could have a bug that forces us to pull functionality out of a chip that's on the market, and thus we decrease our product roadmap. Two, we could go to market with a bug that can't be worked around and can't be fixed, and we literally have to pull the product back from the market. Or we have to spend time and money replacing parts for customers when there's a problem with the chip. All of these are problems associated with risk, because we will go to market when we're not 100% verified. We're going to go to market pretty much when the product is due. So the goal is to have that due date be as low risk as possible. Of course, the highest risk activity you can engage in is trying to debug a chip in the lab after it's come back and after it's not working properly. This will usually happen right around the deadline, and then all the pressure will be on at the time when everybody is looking. This is what we're trying to avoid. And we avoid it by using the UVM. The question is, how does the UVM help us solve this problem? And it does it in two ways. One is, once you get good at using the UVM, you can create test benches much more quickly. You won't have basic architectural questions about how are we going to put together our test bench, how are we going to structure our test bench. That's all been defined by the UVM, and so we're going to code more quickly. The other is that we're going to have a library of agents and VIP that we got from previous projects, and so we'll be able to reuse those things more quickly, and thus we'll have a place to start, so we'll be able to crank out our test benches more quickly than we would be able to. The key first step to all of this is learning the UVM. So here's our agenda for the next 12 classes. First, we're going to talk about SystemVerilog for VHDL engineers. This is going to be to show that SystemVerilog has a lot in common with VHDL. If you already know SystemVerilog and you already know Verilog, you could skip this section. It is primarily here for folks who are just starting out with SystemVerilog and want to get a handle on it. Next, we talk about object-oriented programming, which is the core of the UVM. How does object-oriented programming work? What's the idea behind it? And of course, this is a huge topic. We're going to talk about enough of object-oriented programming to be able to use the UVM. Then we'll talk about SystemVerilog interfaces. These allow us to transfer signals around the test bench and to make them available to the UVM. And then packages, includes, and macros show how we create a project, how we organize the files that make a big test bench. And once we've got all that out of the way, then we can start looking at the UVM. We start by looking at UVM test objects. What are they? How do they work? How do we launch tests using them? Once we've got this top-level test object out of the way, we can start looking at UVM environments that pull pieces of the test bench together. And we can look at seeing how to connect objects within a test bench. Once you're connecting objects, then you can move on to transaction level testing, where we're moving transactions around the test bench. And then the analysis layer that allows us to look at these transactions and use them to decide whether or not the test bench is working properly and whether or not we have enough functional coverage. That leads us to reporting, because if you find errors in the analysis layer, you're going to want to report them. And then also it leads us to functional coverage, because you're going to want to be able to store that data and demonstrate that you've covered everything that you want to cover in your test bench. And then finally, we're going to talk about sequences, which are the stimulus generators for the UVM. And so over the next 12 lectures, we're going to work through all of these pieces and build up from the bottom up to the sequences to be able to show how you can start to use the UVM yourself. That's all for our introductory lecture. Let's get started. Next, we're going to be talking about SystemVerilog for the VHDL engineer.